In this video, we're going to talk about graphs, and specifically, we're going to talk about what graphs are, and we'll talk about some definitions that we're going to use when we're working with graphs. So graphs are non-hierarchical, non-linear data structures, and we'll see some examples of what that means, but they're not like a list that was linear, and they're not like a tree, which was hierarchical. They're made up of two components. The first are the vertices, which is the plural of vertex, and we'll also call those nodes. And we refer to the vertices by a label. So here you can see we have a vertex A, B, we have a vertex C, we have a vertex left, and we have a vertex labeled Chicago. Again, those labels can be whatever they want, and they're not really part of the graph. They're just the ways we identify the graph. Graphs also contain edges, which are the connections between vertices. We refer to edges with a pair of the labels of the vertices that they connect. So if we have an edge from vertex A to vertex F, we would call that AF. If we have an edge from vertex Chicago to the vertex labeled New Orleans, we would call that edge Chicago, New Orleans. So here's an example of a graph. We have 6 vertices and 8 edges. Now this is an undirected graph because the edges don't have a direction. We'll see some directed graphs later. Now we can add a vertex W to this graph, and this right here is a valid graph because it has vertices and edges. Just because W doesn't have an edge to any other vertex doesn't mean that this isn't a valid graph. We just say that it's not connected because you can't get from one vertex to any other vertex in the graph. So now that we've added a vertex, let's add some edges. So we'll add an edge from F to W. We call that FW. Next, we'll add an edge from D to W. We'll call that DW. And the edges don't have to be listed in alphabetical order. We could also say that we have an edge from W to E, edge WE. And so this is the graph after we add the new vertex and the 3 additional edges. So here's another example of a graph, and we're going to talk about some specific definitions. We say 2 vertices are adjacent if they're connected by an edge. So here A and C are adjacent because there's an edge A to C. A to D are also adjacent vertices, as are B and C, and we can also call adjacent vertices neighbors. There's a special type of edge called the self loop, or sometimes you'll see it referred to as a sling, and that's when a vertex has an edge back to itself. So a good example of a real-world application for this is your computer has which you can think of as a vertex, has an edge, which you can think of as a connection to IP address 127.0.0.1, which if you connect to that, you're going to connect back to your own computer. So there is an edge, there is a connection, but that connection is from your computer to your computer. In a complete graph, every vertex has an edge to every other vertex. There's no way to add an additional edge that would connect 2 vertices that are not already adjacent. An incomplete graph could still be connected where you can get from any vertex to any other vertex. However, you may have to go through an intermediate vertex. So to get from A to C, no problem. But here, to get from A to D, we would need to go through either vertex C or B. Now, a path is a series of edges that connects 2 vertices in a graph. So let's create a path A to D to B, and the length of that path is going to be the number of edges there. So we have 2 edges, the edge AD and the edge DB. A cycle is a path that starts and ends at the same vertex. So here we can create a cycle from A to C to D to B and then back to A. So this gives us a cycle, and notice this cycle actually includes all the vertices, but we could have one shorter. We could have ACBA or ADBA or something like that, or even DCBD. Those would all be cycles as well. Now, if a graph doesn't have any cycles, we say that it's acyclic, and you may notice that looks an awful lot like a tree. Here's another example of an acyclic graph with the same vertices. And now we say a graph is connected if there's a path from every vertex to every other vertex. So here you can see there's a path from C to A and from D to B to A to C and so forth. So we can get from any vertex to any other vertex. Here's an example of an unconnected graph. Notice there's no way to get from vertex F to vertex C. Now, if we have a directed graph, that's where each edge isn't just a pair, it's actually an ordered pair. There's a starting and ending vertex. So edges are one way. So AC is an edge, but there is no edge DA. The edge that you see from A to D is edge AD, not DA. So we have edge AB and edge BA, and those are separate edges. So we say a directed graph is connected, just like before, if there's a path from every vertex to every other vertex. However, keep in mind, now these are directed edges, so we have to keep that in mind. So this graph is connected because notice there are edges that allow us to travel in a circle around the graph, so we can start anywhere and wind up anywhere else. But in this graph, even though there is an edge between each vertex, because of the ordering, there is no way to get from C to A or B to A. So there's no path from B to A, and so this graph is unconnected. Another type of graph is a weighted graph, where we associate a weight or a cost with each edge. These edges are represented as a triple. So this would be the edge AB2. This would be the edge DC3. These are undirected, but we could have directed weighted graphs as well. So the weight of a path is the sum of the weights of each edge in that path. So the path ACD has the weight 1 plus 3, which is 4. So here's an example of a weighted directed graph. Again, the definitions are all the same. They just incorporate the fact that the edges are directed. And our triple is ordered now. So the edge from A to B has a weight of 4, but the weight of the edge from B to A has a weight of 2. So these are just some of the definitions we'll be talking about when we cover graphs. It's a good idea to try to memorize these, and there is a list posted on Canvas to help you keep track of all these. Here's an example of a weighted graph that represents the distance between 3 cities, Dallas, San Antonio, and Houston. If we represent this information using a weighted graph, now our program has access to it, and we can perform algorithms on that graph to add intelligence to whatever application we're writing. So for example, suppose we were writing a logistics program that determined what order do we need to visit different cities, or how should we separate a certain sales territory. Information like this is critical to do that, and a weighted graph lets us represent that, and then graph algorithms let us find out information about whatever's represented with that graph. Now this is an undirected graph. A directed graph could do things such as represent fares between cities. So these are the actual airfares between these 4 cities from October 2020. You can see to fly from Phoenix to Chicago, it's $114, but it's $110 to fly back. Whereas between Dallas and New Orleans, the price is $97 in each direction. Once we encode this information into a weighted directed graph, we can use it to make decisions about, for example, what's the cheapest way to get from one city to another. And here we have airfares, but there's no reason we couldn't add additional information, additional edges that may be our train fare, bus fare, and so forth. And with this information encoded into a directed weighted graph, we're able to create applications that provide a lot of information. So think of something like Google Maps or Waze or even an automated car. Graphs allow those types of applications to exist. Without graphs, without graph algorithms, we wouldn't be able to do things like that. Or at least it would be significantly more difficult.